Okay, welcome everybody to CHEP colloquium. Okay, today is a special colloquium. So today we have a very distinguished speaker, Professor Subir Sarkar from Oxford University. Professor Sarkar is well known, also has questioned the standard paradigms, and his contributions to physics of cosmology and particle physics and everything are very, very well known. Of course, he's also an experimentalist. Okay, all right. So, just a brief bio sketch. Professor Sarkar has done his PhD from Tata Institute of, after BSMS from IIT Kharagpur. He did from PhD from TIFR, and then he did postdocs at CERN and CISA before joining Oxford University as a lecturer, and then since 2006 he has been a professor, and recently he has become Professor Emeritus at University of Oxford, Department of Physics. He won several awards, Bruno Rossi Prize, UPAP, TIFR, Homi Bhabha Medal, Niels Bohr Professorship, Weber Fellowship, Advanced Fellowship at UK Particle Physics, and so on actually. And he has been adjunct professor to many international and national institutes, and his theory interests include, which we know it is completely all astroparticle physics, cosmology, high energy astroparticle physics, and particle phenomenology. But what is more interesting is his experiments he has been involved with is CERN W8, WA66, Auger experiment, Ice Cube, of course, CTA, and QSHS. I didn't know this. Okay.
Quantum sensors for hidden sector.
Oh, okay. And LSST. Okay, so over to Subir, and today he's be talking about axions. Over to you, actually. Yeah.
Thanks a lot for that kind introduction. So it's good to be back. Today I want to talk about a problem that I know many of you are interested in, and it's a very well plowed field. So it was actually a bit of a surprise to me when my student Konstantin Bayer, with whom we have written recently this paper here, approached me to discuss this, because I thought anything that could be said about relic axions had already been said. But to our surprise, we discovered that there was actually an interesting point to be made, which also has pretty important implication for experiments. So that's what I'll talk about today. And in fact, one of the experiments we motivated ourselves with our laser physicist collaborators in Oxford, and this was carried out last year at the X-ray free electron source laser at Hamburg. Oh, sorry. Am I within view now? Yeah. And I'll talk a little bit about that experiment towards the end. It's just been accepted for PRL, and it looks like we might be able to probe that parameter space further at a similar X-ray light source which is in Stanford. So I want to start by saying that IRC has special memories for me, because as you know, Rohini was for many years one of the stalwarts here, and she is also one of my oldest friends. We first met as undergraduates, actually as science talent scholars. She was at IIT Bombay, I was in Kharagpur, but we used to meet at summer schools since 1970, and we have been friends ever since. So it was naturally a bit of a shock when she passed away. Well, you all know the history. Well, in that picture, there she is, looking like a kid amongst us all, as she always did. And that's me at the back. And as you see, those days we are all in black and white. Color had not been invented. And all I can say is, Rohini, I think her most important aspect to me was that, as we all know, women in physics have to surmount quite a lot of barriers. And she had many successes, but also number of non-successes, but she was never bitter. I like that about her, that she was a warrior. Yes? She is a biologist. She was from Shantiniketan and she is retired now. I'll tell you about it later. Yeah. All right, so my topic today is broadly about dark matter. I noticed that Tracy Slatier, who was here last week, also showed this picture, kind of impressionistic landscape of dark matter candidates from Tim Tate. I bet he wishes he had $1 every time someone showed this. Today we are going to not discuss the possible variety of particle candidates for dark matter, of which there are very many and you can still add to them. I'm going to discuss a particular class which are axions, and as you can see here, interest in axions has been growing significantly in the last 5 to 10 years, coincidentally with the fact that it has proved difficult to detect weak scale so-called WIMP dark matter. But in fact, both were proposed at around the same time in the mid-80s, and the initial paper that is up here was by Peccei-Quinn, who noticed that there is this issue with the fact that CP violation is non-existent due to the standard interaction, strong interactions, and they proposed a new symmetry named after them, which is spontaneously broken, in order to ensure that this quantity becomes a dynamical parameter which can relax to 0 in its own potential. And after a few months, Weinberg and Wilczek independently noticed that that would mean that there is a pseudo Nambu-Goldstone boson associated with that symmetry breaking. It is pseudo because the axion actually is just like the pion. It has the same quantum numbers. It mixes with the pion, and the pion gets a mass because of the breaking of chiral symmetry when the temperature of the universe drops to the QCD scale from the condensate, quark condensate in the vacuum, and the axion mixes with the pion, so therefore also gets a mass. And that is why it's a pseudo Nambu-Goldstone boson. And it then was noticed that this makes it a excellent candidate for dark matter, for cold dark matter, unexpectedly. And more recently, this field has developed like topsy. And this is from a recent review which points out that these particles are part of a broader class of particles which include not just scalars or pseudoscalars like the axion, but also vectors. And in fact, the range of masses that are under consideration now range very, very broadly. But my discussion will be largely on the QCD axion, because I like the fact that this is a problem within the standard model. It is not really adding new physics for the sake of it, but because it is actually required to solve an extent problem within the standard model, which is rather urgent. And the fact that it's a dark matter candidate is a bonus, and one likes that kind of idea, and it is a additional virtue that the idea is testable. So what's not to like? Now I'm going to give you a broad outline of many topics in the field, but focusing on the issue of the formation of topological defects in the axion field. So this talk is going to range over a rather large number of issues, and in order to keep within time, I'm going to say something rather briefly about each, but you're very welcome to ask me questions about any aspect that you are interested in. So I want to emphasize, because this is something that Sabine Hossenfelder has been saying, that we always add epicycles on epicycles. It's perfectly true that the original Weinberg-Wilczek axion was never found. If you look in Weinberg's paper, it was predicted to be around 100 keV, because he thought that the Peccei-Quinn scale was the weak scale. That is, after all, the only real scale we know in nature apart from the Planck scale. And that would make the axion mass around 100 keV to an MeV. And after a false alarm at CERN, where a group from Aachen thought they had seen it, it was realized that it didn't exist. But then people proposed that the Peccei-Quinn scale could be a lot higher, so the axion becomes extremely weakly coupled and otherwise invisible, and that is very much viable, and that is what then becomes a good candidate for dark matter. So what's the problem? The problem is that we have an excellent Lagrangian that gives us everything that we measure in the laboratory, the standard model. We are now busy measuring the parameters of this Higgs potential, but we understand everything about the gauge fields F, and how they couple to the fermions, and in particular how the fermions get a mass by coupling to the Higgs field phi. But it has been recognized for quite some time that you have the freedom to add to this Lagrangian a term, this theta FF dual, which violates CP. And in the weak interactions, we know CP is violated because the quarks mix, and there is the determinant of the quark matrix, if we take its argument, that phase is a CP violating phase. But there is a much larger contribution possible from this term, which you can add to the Lagrangian without changing anything. It is perfectly consistent with all the gauge symmetries, etc. But physically, what this would lead to would be a neutron dipole moment, which you can naively calculate as just the size of a neutron and the charge of the, it's a UDD. So you can typically take a scale and a charge, and you get a number, and the observed quantity in the laboratory, or rather the upper limit on the observed quantity, is 10 orders of magnitude below that calculation. So something requires this term, which is naturally of order 1, to be less than 10 to the minus 10, very likely 0. And whenever physicists see a number which should be of order 1 but is not, then they immediately think there must be some underlying symmetry that drives it to 0. And that is exactly what Peccei and Quinn proposed. And of course, that symmetry must be broken. And then the idea is that this bare theta plus the argument of the determinant of the quark mass matrix, these are two independent quantities, but they together create this object which can then relax to 0 and cancel each other out, right? And this boson, as I mentioned earlier, is the axion. And as I also said, it gets a mass by mixing with the pion. This has been now calculated quite carefully on the lattice, and this is the kind of number that you'd get. So if Fa was around 10 to the 9, 10 to the 10 GeV, then this would be of order micro to milli-electron volts. The cosmology of the axion is fascinating, and that's what I'll talk about for the next 30-40 minutes. But just to give you a broad outline, because we are going to go to a lot of places and we have to keep track of where we are, the basic idea is that in the early universe, this Peccei-Quinn symmetry is unbroken. Then at some point it is spontaneously broken, and you know how that goes. You drop to some arbitrary point on this Mexican hat potential. The issue with the axion is that at this time, this vacuum manifold is multiply connected. You can get topological defects called strings, one-dimensional defects. But much later, when the temperature drops to the QCT scale, this whole thing is tilted because of the fact that the pion gets a mass, and by virtue of that, the axion also gets a mass through the mixing. And that means one point on this manifold is picked out above any other, and the field then oscillates about this point. And what was pointed out by 3 groups separately is that these damped oscillations of this axion, very weakly damped because it is almost non-interacting, that has the same equation of state as non-relativistic particles. So it acts like cold dark matter. And in fact, the contribution to the density because from axions is written like so. So therefore, if you want dark matter density, which is typically about 0.1 or something, you can see that you want Fa to be around a large energy scale, for which we have really no other justification in nature. The same kind of energy scale also enters in considerations of supersymmetry breaking in a hidden sector, etc. But I think it's fair to say that there is no obvious reason why there should be a new energy scale there. Except that when string theory came along, it was realized that axions are generic in string theory, although the associated scale is a lot higher. It's a string scale around 10 to the 17, 18 GeV. So from this, we can immediately conclude that if the axion dark matter is not to overwhelm the universe, in other words, stop it from expanding to its present size at the present rate of expansion, then the scale has to be limited in this range. And the corresponding axion mass is here between a micro electron volt and something like 0.1 milli-electron volt. And so experimental searches started on this energy range right from the mid-80s, and they have picked up speed recently because WIMP searches started also in the mid-80s, but kind of took precedence because they were motivated by the idea that there is new physics at the weak scale, motivated by the naturalness issue and so on. Whereas the naturalness problem here is of a completely different order. It is within the standard model, not to do with the Higgs quadratic mass corrections and so on. Now, the thing that I want to focus on in this talk is that these arguments, which have been now around since the mid-80s, so for 40 plus years, they have not accounted for the fact that these topological defects like strings and domain walls that form in the axion field also create new populations of axions, and they in fact are not a negligible component. They in fact turn out to be the dominant component. So let me go through that in a little more detail. So I already sketched this out for you quickly. So the three groups that realize this fact that these very weakly coupled particles actually can become the dominant constituent of the universe very naturally, where this Preskill, Weiss and Wilczek, Abbott and Sikivi and Dine and Fischler, and all these papers appear back to back in physics letters. Those days I think science was pretty civilized, and the editor, if he received 2 papers or 3 papers about the same subject, would insist on publishing them together, so that there was no argument about precedence, right? And as you see here, this is the same Mexican hat which is getting tilted, and the angle theta is the misalignment angle of the axion field when the potential first develops. And this potential develops very, very quickly because these are due to instantons in QCD, and their temperature dependence is very steep. There's something like T to the 9 or 10. So as the temperature drops towards the QCD scale, towards a couple of 100 MeV, all of a sudden, almost instantaneously, the axion mass turns on. So this thing which has been flat suddenly gets tilted, okay, within a Hubble time. And then the axion field suddenly realizes it's not at the bottom of the potential, and so it starts oscillating around there, as I said, without much dissipation because they're very weakly coupled. And if you work out what the number density of axions and their energy density is, these are all arguments going back to the mid-80s which are in these papers. You can see that it will have an energy content which is primarily determined by this misalignment angle. And if you then look at what are the constraints on this energy density, I mentioned already that Fa has to be less than some number, otherwise the dark matter due to axions is excessive. People often say the universe is overclosed. Actually, that is technically impossible. The universe cannot be overclosed because we have only one universe and we are here today. So the statement is that we would not be this old and expanding at the present rate if there was more than the amount of energy density that corresponds to omega h square of order 0.1 or whatever. So that puts the upper bound, as you can see, around 10 to the 11, 12 GeV. But you also have to take into account that these axions can be created in standard model processes. They have a coupling to 2 photons, the triangle anomaly, same as for neutral pions. And they are therefore, and they can also have couplings to fermions. So they would be created in stars like our sun or supernova, white dwarfs, or everything. And by insisting that our understanding of stellar evolution not be disrupted completely due to this new source of particle production and particles which also escape from the star without scattering, we would require that the axion scale should be to the right of this green line, right? And so there is this light axion window which is then implicated, and this is where experiments are focused. These laboratory searches refer to the early searches I mentioned at CERN, where people were looking for 100 keV axion, which were unsuccessful. So the bottom line is that we are most of the activity has been on this light axion window. There is one more subtlety, which is that it matters whether this Peccei-Quinn symmetry breaking breaks before or after inflation, and that is shown in this nice cartoon that I got from Kiran O'Hare's review on this, which shows that if the axion Peccei-Quinn symmetry breaking happens after inflation, then the universe is already homogeneous and isotropic. Some little patch has been blown up to be big, and therefore the value of the axion field, the Peccei-Quinn symmetry breaking happens independently at different points here, and the typical value of this theta angle, you have to take a statistical average over all possibilities. Whereas if the Peccei-Quinn symmetry had broken before inflation, then whatever value of theta was picked out at the point of symmetry breaking, that would be covering the entire universe. So that would be some constant value there, okay, without any gradient in it whatsoever. Here there is a gradient. Now, immediately if you think about it, one possibility comes to mind that maybe this initial theta was very small, so that's why there is no energy density in the axions, they don't make up dark matter, but that would require fine-tuning that theta quantity, right? So our philosophy is we started this whole business because we don't like fine-tuning, so you don't want to keep introducing it again and again whenever some problem comes up. That's in poor taste. So, poor taste can't be quantified, or good taste can't be quantified, but I think we all understand what I mean by that. So, if you then do the task of putting together the work of the last 40 years on axion, a nice plot is to ask what limits have been placed on the coupling of axions to photons as a function of its mass. So, here this diagonal track here is the expected theoretical correction between the photon coupling and the axion mass for two classes of models. One is Kim, Schiffman, Weinstein, Zakharov, and this is Dine, Fischler, Srednicki, Zhitnitsky. And as you see, there is a little bit of a spread among them because their models are somewhat different. I'll come to that shortly. But they essentially trace out this track in this plane. Then you have various limits from stellar evolution, etc. up here, and experiments. This one cast looks for axions from the sun, which then they pass through a magnet, a old Leavitt magnet at CERN, to see if they convert back into photons, and they haven't seen anything, so they rule out this region. And then there are various arguments from all kinds of things: early universe physics, BBN, CMB distortions, extragalactic background light, all that stuff is here. And going to lower masses, there are limits. These are more relevant to axion-like particles, which arise in string theory, because this track defines what the mass should be for a QCD axion. These come from different arguments here. And this lot here are the laboratory experiments that are being done using what are called haloscopes to directly convert axions which are right now passing through us, if any of this is true, to try to convert them into photons and therefore actually see dark matter. So this band, as I mentioned, the light axion window where these experiments are focused, is motivated by the fact that in here the relic axion misalignment energy density, the misalignment of the initial axion field, the initial misalignment of the axion field from the minimum of its potential, which develops at the QCD scale. And that gives you this kind of mass range, and that's why all the experiments are here. But in fact, I'll argue that these experiments are looking in the wrong place for the specific instance that I'm interested in. So the experiments look like this. This is the leading one, as you saw in the previous picture. This ADMX is the one that is probing down most and is already reaching the necessary sensitivity for the leading theoretical ideas, models. And basically what it is a large magnet and low temperatures and all that, but that didn't concern us. The basic physics is simply that this axion to photon coupling, which is universal, not model dependent, means that if I provide a virtual photon, which is a magnetic field, then an axion which is passing through that can convert into a real photon. And the mass range that you're talking about corresponds to microwaves. So all you have is a microwave cavity, and you basically tune through it very, very, very slowly, because the axions that are in our galaxy, they are moving around at the typical virial velocity, which is few hundred kilometers per second. So the line will be extremely sharp. The line that you see here, this blip, the Q factor is very, very high, right? And so the problem is that you don't want to tune over it, you want to really catch that. And that is why these experiments take a long time to scan through the available parameter space. And now there are new experiments like this one here, which is in fact using quantum technologies, qubit sampling and so on, in order to speed up this scanning by having lots of parallel arrays of qubits, etc. But these technicalities did not concern us. My point is that all these experiments are focused on this light axion window, and of course they don't get it, they don't see anything, but to interpret that as a bound on the coupling, they have to assume something for how much is the axion density in the room. So you have to make an assumption about the halo dark matter, and they assume some typical number. This is really a bit on the optimistic side. It's really more, 0.3 plus minus 0.1. But whatever it is, they all should adopt the same number so you can compare their sensitivities fairly. And this is the kind of state of play. So the question I would like to pose is, are they actually looking in the right place? Now, why do I say that? Let me give you some background first. So this axion coupling, like I said, the two-photon coupling is there for any model. But the two models that are there, due to these two gentlemen, sets of groups, people, differ in a important respect. In this model, the KSVZ model, there is a scalar field which carries Peccei-Quinn charge and one super heavy quark which couples to that, right? So the number of quarks carrying the Peccei-Quinn charge is just one. Whereas this model, in my view, is more general. It essentially adds a scalar field which carries Peccei-Quinn charge, and all fermions coupled to that scalar field. So all fermions pick up the Peccei-Quinn charge, and therefore the number of particles that are carrying that is larger than 1. Would be, for example, 6 in the, yes. Yeah. 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 Right. Sorry, if I? Correct. Yeah. Huh. Oh, it's very small, because you see this number is 0.97 for KSVZ and 0.36 for DFSZ. It's just a factor of, yeah. Huh? Well, that would, the calculation, it would be quite small, negligible. I mean, it is correct up to the second decimal place. So you can see it's less than 1%. It's tiny. It's not significant here. So when it comes to fermions, however, you can have a big difference. So for example, this axion does not interact at all with leptons. It only interacts with quarks. This interacts with both leptons and quarks, right? So, one might say this is more generic, this model. But UV completions are, a matter of taste. We don't actually have a formal UV completion for axions, but these models are interesting because they provide a concrete realization of this Peccei-Quinn symmetry in a realistic framework. So what happens in the early universe is that after Peccei-Quinn symmetry, as I said, the vacuum manifold is not simply connected. What that means technically is that there's something called the homotopy group, and you have to ask what that group is. So if pi naught is non-trivial, you have monopoles. If pi 1 is non-trivial, you have strings. If pi 2 is non-trivial, you have walls. Pi 3 is non-trivial, you have something called textures, and so on. In the case of axions, you will always get strings at the Peccei-Quinn scale. But then when the temperature drops further to lambda QCD, then you have a discrete symmetry, Z of the coefficient of that is the number of particles or types of particles that are carrying the Peccei-Quinn charge, which would be more than 1 in the case of DFSZ. So this is again a schematic of what's going on. So the strings are created because this manifold here is non-trivially connected. So when you wrap around it, you don't come back to the same point. So effectively there is a bit of space-time actually missing around the string. It's a defect. And the amount that is missing in radians is proportional to the tension of the string in Planck units. So to G times mu. So for example, for a gut string, it would be whatever 10 to the minus 6 or so. That much of space-time is missing. That's why these things do very significant gravitational lensing. Now people have simulated the evolution of these string networks and determined that typically the result of their evolution, interconnection, radiation, they of course can, loops of string can bake off, emit gravitational radiation and axions and so forth. It's a complicated problem, but it has been looked at in great detail now that bigger and bigger computers are available. And the net result is that you have something of order a few thousand strings per horizon, per Hubble radius if you wish, and that something like 1,000. And this is, for example, a recent simulation by a group based at Berkeley, who have used up, it looks to me, a fair bit of the CPU power that they have there to try to create a simulation that is as realistic as possible. And this gives you some kind of a sense of how the gas of strings, you of course have to rescale as the universe is expanding. It's technically quite a challenging problem, but they have a pretty large grid, and they can study the radiation lost from the strings and determine what the spectrum of the radiation is, what the spectrum of the string scaling network is. And they are not the only group. There is also other people, including my collaborators who in Oxford, that is Gorgetto, who has ICTP and so on, and also a group in Japan. People are doing simulations, and they don't all agree with each other exactly, but the general consensus is that the axions radiated by the string work contribute about 25% more dark matter than the oscillations did, right? So, for example, this group published this thing in Nature and said our preferred mass range is between 40 and 180 microelectron volts, and this is larger than the dedicated experiments that are going to test this. So they made a big noise about how they are doing a more precise calculation of the relic abundance, and that actually motivated a new experiment. This is a plasma haloscope called ALPHA, and you see earlier the haloscope experiments were probing here. They are now motivating somewhat heavier axions because of the additional contribution to the axion relic abundance from the strings, and this is now the focus of attention. And the point is that these theoretical calculations of the relic axion abundance should be taken seriously, because that is, after all, that defines the lamppost under which you look. Otherwise it's a huge phase space. You would not know where to look, right? By the same philosophy, if I were to find another contribution to the relic abundance of axions, which would implicate a different mass range, then I would argue similarly that we have to take that seriously in terms of experiment. And that's exactly what I'm now going to do. Oh, these things are whipping around at the speed of light. So when they cut each other off, intersect and create small loops, those things vibrate. Within a Hubble time, they would have decayed away. They also create gravitational radiation. So you have to look in detail as to what is the dominant energy loss rate. Typically, in this case, they're mostly going into into axions. However, this is not enough. This is a step in the right direction, but this has ignored domain walls, which form in the post-inflation scenario. So here now I've added one more picture to that cartoon I showed earlier. So up to this point you just set cosmic strings, but now you see you're tilting that potential, and now you have a Zn symmetry, because there are n objects that are charged under Peccei-Quinn. So when you have a discrete symmetry with n minima, and there are potential barriers between them, those potential barriers are topologically stable. You can't get around them, and they contain the energy density of the original symmetric vacuum. And so that energy is evidences itself in the shape of domain walls, which are flat sheets. They are as thin as the inverse of the scale that we are talking about here, and they are also whipping around at the speed of light, right? Now we're kind of entering into science fantasy, but mathematically these objects exist, and incidentally they're seen in condensed matter systems. So this is not all make-believe. You see them in superfluid liquids, you see them in liquid helium-3 and so on. And actually some of our understanding of their evolution comes from the condensed matter colleagues. I mean, they are doing non-relativistic stuff, but the same physics really. You can also have complicated systems, in fact not can have, you do have complicated systems of walls bounded by strings, and you can study all this by solving the semi-classical equation of motion, as I'll show you. So if you have more than one quark charged under the Peccei-Quinn symmetry, then you have the formation of domain walls at the QCT time scale, which is about 10 microseconds after the Big Bang. Now the significant thing about walls is that their energy density goes as 1 over time, whereas for both matter and radiation the energy density goes as 1 by time square. In other words, they decay away much more rapidly than the walls. The walls will come to dominate, and so the wall network will start to dominate the expansion of the universe at a time which you can work out from the wall tension, and this will typically be some number like this around the time of late end stages of nucleosynthesis, right? So we can't let the domain wall come to dominate, because once it comes to dominate, it will drive inflation, power law inflation, not exponential, but bad enough, because this is inflation without end, right? And it will just create an empty universe, and even if the domain walls then decay, they will deposit their energy in localized places. Now, unlike the usual model of inflation where you have some oscillating scalar field which is dumping energy uniformly all over the universe, this case is unacceptable. It will not give us anything like what you knew, right? And this cosmological domain wall problem was first identified by Soviet physicists Zeldovich, Kobzarev and Okun. And in this nice paper in 1974, they were actually concerned with spontaneous violation of CP. But I can just cross out CP and write Peccei-Quinn symmetry, the same conclusions hold. And they said, if there is no mechanism that leads to the disappearance of domains at sufficiently early stage of the evolution of the universe, the domains would lead to conclusions which are in contradiction with the experiment. The kind of modesty saying that it would lead to the lack of an universe. That's basically what it is. This is a serious problem. So either the model of spontaneous breakdown of Peccei-Quinn symmetry or CP symmetry is false, or there must exist mechanisms which facilitate the disappearance of the domains. And this is a very powerful constraint on many extensions of the standard model, where discrete symmetries are generic, right? You have to worry about the cosmological domain wall problem. But Pierre Sikivi realized this. He's kind of worked on axions since the beginning on every aspect, and he says, look, why don't we just introduce an interaction that breaks the discrete symmetry slightly and tilts the vacua, so one of them is picked out as more favored than the others, and in that case the domain walls will disappear. So we'll see how that happens and why Sikivi's solution does not work. But first I want to emphasize that when Konstantin Bayer, my student, came to me, I said, look, they have just been writing all these white papers and all kinds of stuff about this subject. What do they say? And to our surprise, this white paper in SNOMAS, which was written by everybody working on axions in the business, says while the phenomenology of strings domain walls has been studied extensively, no consensus has been reached. Now this surprised me, because it seemed to me that the conclusion was pretty obvious. So that's why I decided to look at it. But this was the word of the experts. And more interestingly, I went to a workshop in Florence, and Mike Dine was there, and Mike, take him seriously, and he says this domain wall energy density problem is not a problem, because he says that this energy will go into extremely relativistic axions which don't contribute significantly, in the sense that they would be redshifted, so they don't contribute to the present energy density. In fact, there is a flaw in this argument. The flaw is that, sure, they can be initially relativistic, but ultimately they will turn non-relativistic when the temperature drops below their mass, and then they will start contributing to cold dark matter, right? This origin is quite different from the oscillations of the axions, which are also cold dark matter. They were born cold. These ones were born hot, but then turned cold. But this contribution needs to be accounted for, and before you do that, you can't make a statement about whether they're important or not. This is always in the post-inflationary case. That we'll see, we'll calculate. Right. So for that, you have to follow this evolution and collapse of the domain wall network. So in more detail, that vacuum that I drew earlier, now imagine it being corrugated. There are n vacua in here, and each one has got this domain wall separating them. Okay, and so a typical profile of the domain wall would be something as sharp as that in field space, which you cannot go through. The barrier is too high, and you cannot go around it. So it is stable if this number is more than 1. If it is 1, then the network that forms disappears, so this is not a problem. And these domain walls will only form when the Hubble parameter drops below the axion mass. So here is a toy example of how a domain wall forms. Supposing I have a Z3 symmetry, 3 vacua, and I just look at a honeycomb and I number them 1, 2, and 3 at random, then you can see I can always draw a line that separates all the vacua marked number 3 from the ones marked 2, right? So these are domain walls that you can see. This is the kind of thing you will see forming in a condensed matter system. And here is a simulation that Sikivi and collaborators did of domain wall formation actually in a pretty big lattice. This is the Hubble radius on the same scale. And typically, as you get one wall per Hubble volume. The rest of, there will be more walls initially, but they will annihilate each other, and there's only one long wall left that stretches across the sky. Now, how do you know all this? Well, you can write down, just as you write for a scalar field, you can write down a semi-classical equation for the evolution of the domain wall in terms of the potential that you have for the field. And the potential you can take to be some classic Mexican hat-like potential, and we write it in conformal time, which is usual time divided by the scale factor. So you're taking out the expansion of the universe. And the problem is that when you write down this equation, on the right-hand side, the gradient of this potential in terms of the field is multiplied by a squared term. We have converted everything to eta to make it kind of scale-free, scale invariant. But this a square is not scale invariant, and what happens is that as time goes on, this barrier keeps increasing in height, and so this means that in co-moving coordinates it gets increasingly narrower, and you can't resolve it. This is a numerical issue. So the solution that was proposed by Press, Pergel and Ryden, this is the famous Press of numerical recipes. He comes up with these smart ideas. He says, look, why don't we just, instead of a square, call it a to the beta, right? And instead of this 2 here, call it alpha, and set beta equal to 0 and alpha equal to 3, then you also have momentum conservation because you have to obey the sum rules, but that would then not give you a wall that is getting increasingly narrow as you go on. And we checked that actually their idea works. Over a limited range in conformal time, you get the same results as for the physics case, which is here. And in fact, we found to our delight, this was work done by my student Sebastian Larsen some years ago in 1993, I think, that you get something that Tom Kibble had always said should be there for topological defect networks. You should get scaling, the typical correlation length, which is proportional to some number times this conformal time, and the co-moving area of this wall network should scale as basically 1 over eta. Inverse of the conformal time, and this was based on simple arguments which Tom was good at, and actually we found from our simulations that we got a number for this exponent which was pretty much 1 within the uncertainties. We only had a 128 cube grid. Today they have 2056 cube grids, right? But a good analytic argument is always worth a lot of CPU power, right? And in fact, Mark Hindmarsh approached the problem differently. He looked at the condensed matter literature, and he found a way to do a relativistic generalization of the scaling models that they had developed for defects in condensed matter, and he came to the same conclusion that it should go as 1 over eta. Yeah? Not very much, because as long as it is generically of a Mexican hat potential, that's all it matters. You can parameterize it by some wave and some height, that's it. As long as it's not multiple valued or pathological in some way, and it won't be here, it doesn't matter. So what matters for the potential is really the fact that this symmetry breaking for the discrete symmetry that Sikivi sort of invoked is actually quite natural, because Peccei-Quinn symmetry is a global symmetry, and we are told by our quantum gravity friends that quantum gravity does not respect global symmetries. Now, actually, it will turn out that there is some debate about whether that's a theorem or it's just a conjecture. We don't care. Something has to violate the global symmetry in order to give the tilt, otherwise our universe doesn't exist, so you better believe it. Okay? And what I'm going to do is to put an experimental bound on the problem from the other side. So our argument is actually entirely model free. So typical quantum gravity suppressed non-renormalisable operator would have a form like this. It will have some dimension more than 4, as you know, and the order of the operator here has been parameterized as so. And what that means is that this potential, which I had earlier written in that simple form, now gets an additional term, this mu, which is the degree to which the potential is being tilted, right? So mu will be some tiny number like 10 to the minus 12, 13 something, because the order of this operator is large and you have Planck mass in the denominator. Observe that there are two numbers here. One is this coefficient g and the other is this phase delta. These are all properties of whatever fundamental theory actually breaks the global symmetry, the theory of quantum gravity, which of course I don't know anything about. So I should be prepared to acknowledge that g and delta may not be one, it will be some number. For example, if these are instantons, it could be even a small number. So we'll see numerically how things work if you let them vary by say a factor of 100. But first thing I want to emphasize is that numerical simulations done by, as I said, Sebastian Larsen and Peter White, who are my collaborators, showed, this was back in '97, that indeed you enter a scaling regime. This is the area versus conformal time, and then the wall network collapses, essentially because as you are expanding, your horizon is encompassing new bits of vacuum that were initially out of causal contact and now are coming within your causal region. And what you will find is if one vacuum is favored with respect to the others, then eventually that vacuum is more likely to come into your horizon than any other, and then that means that it can be no wall because it's the same vacuum. So the wall network at that time collapses, as you see here, exponentially. And in fact, the simulation was good enough to even show the emission of the Nambu-Goldstone bosons of this scalar field. These little glitches correspond to that. So the wall energy has to go somewhere. It is emitting its own quanta in the process of collapsing. And this is a simulation that Steve Abel did for us on Mathematica. We looked at another case where there is a Z3 symmetry. This is a property of the so-called next to minimal supersymmetric standard model, where you try to solve the mu problem by allowing a singlet field, which is a Z3 symmetry, and that is what addresses the mu problem. But it also creates a domain wall problem. So in fact, we argued in that paper that the NMSSM solution to the mu problem is ruled out because of that. Anyway, the wall network will collapse, and of course the more you tilt the wall, the potential, the sooner this will happen. However, if you tilt the potential, if you break the symmetry, then you are resuscitating the reason why you introduced the symmetry in the first place. I mean, there was a reason why you put in that symmetry. You wanted to solve the strong CP problem. You want to stop the neutron from getting a large electric dipole moment. If you go around breaking the symmetry, then that problem comes back. And since there is an upper bound on the electric dipole moment of the neutron, there is an upper bound on how much tilt you can put, right? So now you see where I'm going with this. There is a lower bound on the tilt necessary to solve the cosmological problem, but there is an upper bound on the tilt necessary to respect experimental constraints on the neutron EDM. And if you put those together, then we find that that order of that operator, which of course has to be an integer, so that is plotted here, as a function of the Peccei-Quinn scale, it has to lie on this orange track in order to be consistent with both these constraints. And even if you allow tuning of that coefficient g or that phase delta by a factor of 100, you get a slightly different track, but not that different. You can still see there's a powerful constraint. And this is in fact what's popularly called the axion quality problem. If you have a high scale for the Peccei-Quinn symmetry breaking, then you have to ask, how do I protect this against quantum gravity effects, which in potentially can violate the global symmetry? And many operators can do that. But according to this, the operator has to be constrained so as to respect these two bounds. And we'll see what the implication of this is for the dark matter. Just to say that our computer in '97 was not very big. Now there are huge computers, and various groups have been studying this problem. They make nice color pictures of the wall string network and so on, and which essentially confirms everything I've so far said. They also see the same scaling with the inverse of the conformal time. They can do more. They can determine the spectrum of the radiated axions and determine the typical relativistic gamma factor of the axions, and that turns out to be of order a few. Okay? We took it conservatively to be 100. They find it to be more like 3 or 4. It is not very, very large as Michael Dine thought it might be. Okay, that's ruled out. The spectra of gravitational waves can also be computed. It turns out to be subdominant. So here is the bottom line. The axion wall network must decay, otherwise there is cosmological disaster, but that generates non-thermal axions, which then are initially relativistic, but subsequently turn non-relativistic. This axion population has never been considered for structure formation. People have looked at the cold axions, which are like cold dark matter. Axions can also be hot dark matter in other contexts if they're massive and thermally coupled. But this is a curious case which has, the implications of this for structure formation need to be worked out. But here I'm showing you the energy density. You notice the orders of magnitude versus the time, right? And what is plotted here are various components. So for example, the photon that is here, that is, as you know, going as 1 by a to the 4. Then you have matter, in particular the dark matter, which is this orange line, okay, that is going here as 1 by a cube, different slope. Here is the axion, which is in fact going flatter initially, but then it collapses exponentially. And when it collapses, it creates relativistic axions. So they're initially parallel to the gamma line, but then they change their slope once the temperature drops below their mass. And we require that they should not exceed the line of dark matter. They can of course be below it, but we are trying to get a limit. So we are let all the dark matter be in the form of these axions from domain wall decay. We also calculate the spectrum of gravitational waves, which you see here is orders of magnitude below, also scaling as 1 by a to the 4. So basically, when we put this together and ask, in order for this decay population to be consistent with the observed dark matter density, when does this decay have to be? The answer is, it has to be almost immediately after the walls form, basically back to TQCD. We are essentially forbidding the formation of the domain wall network at all. And that's a significant improvement over the original argument by Sikibi, who said, well, it's fine if the decay by the BBN, by the time that come to dominate the universe, or by Big Bang nucleosynthesis, which is typically the kind of time scale you think, whatever happens before that, who knows. But actually, in this case, we can require it to happen much earlier back. So these are the points to acknowledge that the gravitational wave radiation is negligibly small, and that this time at which the axions become non-relativistic, that of course depends on how relativistic they were to start with. So this K is the energy of the axions in ratio to their mass at the time when they were born from domain wall decay. That's something that the simulations have to show you. We take a number like 100 to be conservative. As I said, the typical number that is found is a lot smaller. So if the tilt is large enough to make this domain wall decay cosmologically safe, as Zeldovich and company told us we should do, then the breaking of the symmetry should be not so large as to violate this neutron bound. So here you have constraints from various things. If mu is more than mu, remember, is the tilt of the potential, that prefactor in the potential. If that is too large, if it is to the right of this line, then you have too large a neutron electric dipole moment. As the experiments improve, this line is being pushed to the left. This part is ruled out by having too much dark matter. It is in excess of the dark matter that we observe. This track is for K of 100, fairly relativistic axions when they're born. This is the track for a number which is more in line with what the simulations are actually showing. Okay? And so you can now see where we get a constraint that if I also, okay, one more point, if I am allowed to tune those coefficients of the non-renormalisable operators, then I can go from here to there. Okay? I still stay within the plot. So if I am as conservative as possible, if I am as conservative as possible, then I take K of 100, but we give our answers in terms that you can scale. We'll get that Peccei-Quinn scale has to be less. You can read off from here 5 times 10 to the 8 GeV, and that is according to a fraction of axions in the form of dark matter, which is taken to be 1, most conservative. typically you could argue that no more than say 10% of the cold dark matter can be in the form of axions like this. So that would improve the bound, but all this gives a lower bound of 11 MeV, milli-electron volts, okay, for the case of the DFSZ axion. Now 11 milli-electron volts is a long way to the right of the region where all these experiments are looking. And this means that we need to start looking for axions in this mass range where there are very few experiments. There are upper bounds from solar arguments which are actually, and supernova arguments which are now being re-examined to take into account all the uncertainties in the calculation of the axion production in those objects. But currently the only experiments that are operating or are scheduled to operate in this mass range are these few here, right? There is this light shining through walls experiment which is DAISY called ALPS, and there is IAXO, which is the successor of this CAST thing. This is Axion Observatory, and then there is the baby version which is just under construction, and in future they want to go to IAXO Plus. So you can see there is actually very little action in this range here. So we decided that we would in fact look into what could be done in this mass range. So what is being done at Hamburg right now at DAISY is that in the Hera tunnel they're reusing the magnets that were used for the old experiments to do a light shining through wall, which means that you have a laser, you create in principle you create axions by passing it through a strong magnetic field, and then you put a wall in the way. Light can't go through the wall, but axions can, and then you put another magnet on the other side and hope that this axion will reconvert back into photons, which you can then detect, right? And this so far of course there's been no signal. They're just installing this experiment at the moment, and baby IAXO is doing the same thing, except that it doesn't try to create the axions. It looks at the sun, and the idea is that by the Primakov process axions are being created in the sun. They would be at X-ray energies because the inner temperature of the sun is quite high, and they would then be detected when they convert into photons as X-rays. These are both, this is like near future, this is really a few more years, and IAXO and IAXO Plus are more far future. So in my remaining, can I take 5 more minutes? Yeah. Let me just talk about this experiment that we have just done last year at this free electron laser in Hamburg, which is basically they take the beam from Hera, whatever it is, 25 GeV electron beam, and take it a few kilometers to a new site where it is used to create this very, very intense beam of X-rays. And the idea for what we are doing actually came from Buchmüller, who some of you know, who was a DAISY theorist, and who, well, this quite some time ago. I don't think this was long before this XFL was even conceived of. But we realized that what they are proposing is that instead of a magnet, why not use a crystal? Because in a crystal you can have a huge electric field, right? And of course magnetic and electric fields are the same thing, right? So the equivalent magnetic field to the kind of electric field in a crystal is of order 1000 Tesla, which is huge. Now of course it's over a tiny scale, right? These magnets are typically like a, big, and you want, what matters is the field times the distance through which the axion will traverse. But actually, because this thing is at least 100 times bigger than a typical magnet that you can have in the lab, you actually make up for that, and you typically have the same integrated field strength times distance. So the idea is that you take your incident photon, you have two parallel crystals here. These are germanium crystals. You can see one here and one here, which my experimental colleagues, this is led by Gianluca Gregory, I'll show you a picture in a minute, at Oxford, and they convert, the idea is to convert this photon to an axion, and then to have that propagate through this shield between the two crystals to a parallel crystal where it can reconvert back into a photon, and then you look for it. So it is also a light shining through walls experiment, except that we are not using magnets, we are using crystals, right? So as theorists, all you need to know is that these guys know what they're doing, and what they tell me is that if in fact axions were being created by this, then obviously they would be coming along the same line of sight as the original photon. And in this picture, that is this blue spot in the center. So if any of those photons are being converted into axions, once I put in that shield, then of course this blue spot stops. But anything that is converted into axions and reconverts into photons would be in that direction. But as you see here, we saw a few scattered photons, but they were nowhere near this central point here. So in other words, we have zero counts, no conversion to axions. And these are systematic estimates of what kind of a signal you would expect in terms of counts had there been conversion of these photons into axions. The mass range that you would be sensitive to for axions would depend on the Bragg angle of this reflection, and that is given here. But you can actually tune the angle slightly away in order to probe masses which are nearby. That was a clever idea that they came up with. So the bottom line is that now in this GA gamma gamma versus the mass of the axion plot, we can now rule out a large chunk, which is this pink region here, by the fact that we don't observe any events in the very first run, okay? And also can rule out individual masses where we could tune the crystal away by delta theta away from that Bragg angle and sample therefore other masses. And these are other experiments which I'll mention in the next slide, which have also been probing this mass range, but they are not actually axion searches. They are laboratory experiments, beam-dump experiments, which we can reinterpret in terms of axial limits. And these are my collaborators. That's Gianluca here. So the two other experiments that have actually taken data that can be used for this purpose are Babar, and there these people have kind of recast their bounds on, they were looking for dark photons, but you can recast them into a limit on axions that might have been produced by considering processes like these. And NA64 is a electron beam dump experiment at CERN, where they dump 100 GeV electrons on, I think, a copper beam dump to produce axions. And again, they look for both spontaneous decay and missing energy in the final state. And they also put bounds. But our bounds are actually competitive with theirs, as you see, from the very first run. Those bounds resulted after several years of data taking. So I hope that will make the case for us to get a bit more time on either XFL at Hamburg or on the facility at Stanford in order to prove further. So to summarize, we have a problem, domain wall problem for QCD axions when you have the Peccei-Quinn symmetry breaking after inflation, which is typically the case because inflationary scale and the Peccei-Quinn scale are expected to be ordered so. This domain wall network will come to dominate the universe, which is unacceptable. So you have to destabilize them, and the most likely candidate for that are these tilt due to Planck scale suppressed operators. There is another mechanism called bias, which is that a lightly coupled field like the axion undergoes a random walk during inflation, so it is not necessarily at the maximum of the potential afterwards, and that can create one vacuum to be favored over the other. But in this particular case, there is a huge hierarchy between Peccei-Quinn scale and the QCD scale, so that mechanism is irrelevant. So the domain wall network will then decay away because of this tilt, but this also generates a dipole moment for the neutron, which we don't see. So therefore, when you put all these things together, you get a robust bound that the mass of the axion must be greater than of order 10 millielectron volts, which is a factor of 100 higher than where people have been looking for it. And direct experiments targeting this mass range are therefore now relevant. We have put in a new entry, the laboratory accelerator experiments. Of course, they are not limited by the mass they can explode. So it is worth thinking about how we can recast existing laboratory experiments. We've been looking for weakly interacting particles, dark photons, etc., in terms of axions of this mass. And I just want to say, as a kind of a teaser at the end, I'm sure one of you is going to ask me, isn't an axion of this kind of mass and Peccei-Quinn scale ruled out by SN87A? Indeed, we also worked on SN87A, but the point is that the production of axions in a neutron star is not straightforward to calculate. There are large uncertainties because you don't know the equation of state of the core of the star, where they would be largely produced by the Urca process. And but leaving that aside, there are people who are looking at it more carefully, taking into account plasma effects and so on. There is a claim that actually we see anomalous energy loss from stars. Now that of course is a statement of the same order. You have to know, when I say I see anomalous, you have to know what the standard stuff is very accurately, and maybe that too is uncertain. But there is certainly a claim that axions of this mass range could be implicated for explaining observed energy loss from stars. If so, then this mass range is the interesting mass range for axions, and we need to think of more, both experimental ideas to probe them further, as well as think of other directions, astrophysical, cosmological, etc., to try to constrain them or pin down their properties. So I'll stop there. Thank you. Yeah. To some extent, yes, this was, but then of course you have to ask how expensive the crystal is. This is germanium. So it was actually relatively cheap because this technology is well known. Here. So this crystal, this one here, this little crystal here, that's all you're using. So germanium is, as you know, very high atomic number. The atom spacing is what determines the level of the field. So yeah, we discussed possible targets, and Gianluca told me this is, practically the best thing we can do now. But yes, you really could get a factor of a few there. But the real problem, well, I forgot to mention that. Doing the experiment, we had a lot of problem with the heating of the crystal. Okay, so that is really the bigger barrier. You have to find some setup, so we couldn't take data for more than a very brief time. Okay, otherwise the crystal would have burnt out. Huh? Exactly. So they are now trying to figure out a way in which they can cool the crystal or use a different material for that reason. Okay, because the integration time increases, then obviously signal to noise increases that. Okay. So this was really a proof of principle experiment. Okay, and the fact that we already got down within striking distance of existing bounds, which have taken a long time to do, was quite encouraging, which means it's worth pursuing this further. There was a previous experiment by Yamaji here in Japan, but they didn't have this X-ray lasers. So this is very new technology. There are only 3 of them in the world right now. The one at Stanford is just the competition for time has just started on that. Yeah.
Yeah. So if you go back to that plot of the evolution of the dark matter density,
yes.
and where you had a plot of gravitational waves. No,
sorry. Yeah, I know what you mean. Sorry, this one. Yes.
Well,
oops.
okay. That's.
Oh, what happened to mine? 1 second. Anything come? Yeah.
Yes, this one.
This one.
Right.
Yes.
So when it becomes no,
it's okay. I'll just go back to this.
Yeah. So when it's so that the point at which you can really tune that number, right? Where the point at which it transitions from.
Yeah, that number is determined by k, as it says here.
Right.
This one here.
But so is there a cosmological bound on that? Because I mean, I could have thought of a situation where it happens very late.
Yes.
And there is, because this is this will be a spectrum, right? The velocity distribution will be a spectrum.
I understand.
And therefore it can have like downstream
right.
effects on structure formation.
What you're saying is that if I keep them relativistic for longer, they will lose more energy by redshifting.
Yeah.
And then it's not a problem. You can read off from here. I've taken k to be 100 to be here. If I take k to be 10 to the 6, then it will happen later, and then the constraint is weaker.
I see.
Because the simulations are saying k is actually of order 3. I've already been very generous here. Right?
Okay.
So that was precisely what Dine was going on about. He was saying that if he thinks that walls have got huge tension, so what if they emit axions at extremely high gamma factors, right? So but you can see from that later plot that the gamma factor, we can actually read off from the next one, that the gamma factor would have to be something like 10 to the 8 in order to evade the bound. And that is actually not quite possible. So you see here, this is for k of 5, this is for k of 100.
I see.
Right?
Okay.
If you want to actually go back to the typical axion scale, which is around here, you'd have to go from here to there. Right? And this is going as the square root of k, because that went at k square. So you would have to go to something like, I estimate, 10 to the 4, 10 to the 6, 10 to the 8.
I see.
So unless you find some way to motivate why domain walls should emit axions with a huge gamma factor, this is not possible.
So the second question is about the scale itself. So the claim is that it should be less than 10 to the 8 with some mass of
that is reading up from this point.
Yeah. So in principle, if unless there are other bounds, I can that scale can go down to a TeV or something, right?
It can go down much further, yeah.
And so there are no other bounds on that, because I mean at a TeV scale,
at a TeV scale, the axion starts becoming visible.
Exactly.
This was the original axion that was ruled out, whose mass was between 100 keV and MeV. You would then expect to see it in beam down experiments.
Okay.
But in fact, as I said, the only experiment that was done at the time, this is, you're now going back to 1978, 79. Somebody called Helmut Feisner at Aachen, he did an experiment, and actually he thought he saw axions. So for some time in CERN we were calling them axions, because only Aachen people had seen them. But then it turned out to be punched through neutrons or something. Right? Now that kind of experiment has not been done subsequently, and recently, now that everything is up for re-examination, people are asking again whether an experiment like that is an axion around a 100 MeV, 10 MeV still feasible. I saw a recent paper with that title. Right? Now, there are cosmological reasons why you might find that to be unpalatable, but experimentally, it's an open question. Yeah.
So let's say if we ever measure the neutron-electron EDM,
right,
would that tell us something about this tilt?
Yeah, absolutely. So that is in fact a nice question. Thank you. So as you can see, you can read off from this thing here. This is the current, then I have to go to the previous plot, which is not here, this one here. So this was based on the current bound on the tilt, which is about 10 to the minus 9 or whatever it is. These experiments, the people tell us they can easily go another factor of 20 currently. So the more they push down, the more the order of the operator that is necessary to cause the destabilization, more it becomes fixed. So in other words, instead of having this range here, you would make this smaller and smaller, and then you would actually pick out a particular operator, say dimension 9. Okay? So that would actually be a very interesting clue as to whatever is the theory that is giving you that violation of Peccei-Quinn symmetry. So actually, I mean, thanks for asking that, because a friend of mine who does this very difficult neutron EDM measurements was telling us, we've been looking for the damn thing for years and just keep setting upper bounds, and like, when will it ever stop, right? I said, well, you can actually get to the point where it means something rather than just setting an upper bound.
So in the beginning you showed a experiment where the axion is supposed to come, interact with the magnetic field, and the photon is supposed to come out. And the photon is supposed to be in the microwaves.
Right.
So if I make a microwave map of the Milky Way and subtract all the background via modeling, shouldn't there be a glow due to the interstellar magnetic field present?
Absolutely, but that glow, people have all thought about that. It's orders of magnitude below the foreground emission from the Milky Way, because the Milky Way is full of cosmic ray electrons spiraling in the magnetic fields, emitting synchrotron radiation, which is also polarized, and that intensity. So typically, let's say at some typical frequency, 4 and 8 megahertz, which is a typical frequency that the Milky Way has been mapped at, that foreground emission is of order 300 Kelvin. The signal you're looking for is about a micro Kelvin. Okay, so it's about 8 orders of magnitude below. You can't see that. This idea might, however, work better when we look at clusters of galaxies. Right? Again, you have the same thing. You have non-relativistic, non-thermal electrons gyrating in magnetic fields, giving synchrotron. So the extent to which you can model that foreground then becomes crucial. And then you're asking if there is any excess on top of that. I don't know of any situation where it is possible to get within striking distance or reliably do so. But it's worth thinking about it, because there might be some context, some environment where we can model the foreground. This is the bugbear, for all these signals. At first sight, actually Sikvi at one time even suggested that this power law spectrum of axions from these decays can actually give you a extragalactic background that is also a power law of radiation. And the interesting thing is that that's also polarized radiation. In astrophysics, anytime anybody sees polarized radiation, they automatically assume it's synchrotron because they don't know of any other source. Of course, if you tell them axions could do it, they'll say, go away, axions are some hypothetical particle, who cares about that? But actually, to be serious, we don't really know of any other solution to the strong CP problem, and people have thought about it very hard. And for example, if one of the light quark masses could be 0, then you could just rotate it away, but that's not possible. Current algebra won't allow it. Some rules won't allow it. And I think it's still worth thinking about it, but I don't know of anybody who has come up with an alternative solution. So this is why those papers I showed you have 7,000 references, citations because it really is a very attractive solution. And the idea that there is a new light particle is also generic in UV theories like string theory. I've exhausted them. Yeah. Thank you.